Hi, everyone. Welcome to our Cerebellar seminar series. As you know, the cerebellum contributes to both control of movements and cognition. For example, in humans, cerebellar damage not only produces ataxia, but also impairments in planning, blunting of affect, and a variety of linguistic deficits. Today, we're going to hear from Djaina Satoer and Ruben van der Giessen. Djaina is a clinical linguist and assistant professor at the Department of Neurosurgery at Erasmus MC in the Netherlands. She received her PhD 10 years ago in Rotterdam, studying long-term effects of awake brain tumor surgery on language and cognition. She's the founder of the clinical group on brain research on linguistics, and her research focuses on the detection of aphasia in patients suffering from tumors, including cerebellar stroke. Ruben is a clinical neurologist, and he's going to start the presentation today. Also at the Erasmus MC, he received his PhD in 2007 with Chris Dizeu, studying gap junctions in Oliver's cerebellar system. And he started this study that we're going to hear about today, CODECS study, 10 years ago, which focuses on the cognitive functions of the cerebellum by researching patients with isolated cerebellar disease. Thank you both for your time and presentation today.
Thank you very much, and thank you for the invitation. I'm happy to speak with you about our CODECS study. CODECS is an acronym for cognitive deficits in cerebellar stroke. And we started the study in 2014. So first I tell you something about the background, which will be probably familiar to most of you. The cerebellum has a unique architectural structure in the brain with uniform cerebellum modules, which provide an enormous computational capacity for the brain. And its traditional function is controlling motor behavior with two aspects. One is the control of movements to smoothen and give refined movements. And second, the prediction of motor behavior. So the motor learning and the storage of specific movements. Now there are also that are cross connections. And because of these cortical connections, there has been the concept of non-motor aspects of the extrapyramidal system. So in the clinic, we recognize in, for instance, Parkinson patients that they also have a lot of non-motor symptoms. And in recent years, the focus has been more on these non-motor aspects. But in cerebellar patients, this is still quite unrecognized. And I think that there are a couple of reasons for that. First, that the cerebellum is a parallel system to fine-tune motor behavior rather than generating direct motor output. So with a cortical lesion, you have, for instance, a paralysis, which can be in clinical setting really obvious, while the fine-tuning and coordination of movements is much more difficult to recognize. Another reason is that the brain has a plasticity, but specifically in the cerebellum, there's a lot of plasticity, which leads to patients that have severe motor problems with coordination, and within a couple of weeks to months, they can adapt quite easily and have less symptoms. And that also is true for the non-motor aspects. And then there is finally the developmental aspect. We see a huge difference between children and adults. For instance, in language, you see in children that there is a cerebellum mutism, which is quite rare in adults. Now, all these non-motor aspects have led to the phenomenon that we call the neurocognitive cerebellum. And this was captured in the term Cerebellar Cognitive Affective Syndrome, which was proposed by Jeremy Schmahmann. And indeed, several studies have shown that cerebellar patients have problems in executive functioning, in attention, in visuospatial cognition, and affective behavior and processing, and also in language. But the problem with these studies so far is that with mild deficits, you either need to have really sensitive tests or a huge sample size. And all these studies, or most of these studies, have mixed patient groups. So, for instance, patients with tumors and stroke, or neurodegenerative diseases like SCA. And also another problem is that these patients have been measured in various times post-onset. So some have been measured in the acute phase and others have been measured in the chronic phase. And so we thought that there was a need for a larger clinical study with a really homogeneous group. So that's why we started the CODECS study with also Djaina and Peter Koudstaal. And we had a very strict inclusion criteria. So the patients had to have a solitary cerebellar stroke, either a bleeding or infarction. And this stroke had to be proven by localizing clinical symptoms and or neuroimaging. And there had to be no previous history of cognitive disorders or language deficits. Now, the design of the study is that people were admitted at the hospital with a cerebellar stroke, and then they were recruited. We did a neurological examination and fluency tests, and then after 3 months, the patients were seen at the outdoor clinic, and in that time they also had neuroimaging to confirm the isolated stroke, and they also had at 3 months the neurological examination and neuropsychological tests. And then after 3 months, so 6 months post-stroke, the same tests were repeated. Now, our testing protocol was a broad set of neuropsychological tests to have all cognitive domains. And so we did the executive functions. We measured with the frontal assessment battery, the Stroop test, and non-verbal fluency test. Mental flexibility, we tested with the trill making test, and language production, we tested with fluency tests. And then there were several cognitive domains that were tested with the MoCA test. Also, we did a HATS depression scale to exclude patients with depression. And we did an ataxia score, for which we used the ICAR score. That is the International Cerebellar Ataxia Rating Scale, to see how the motor coordination was. And we did some general stroke tests like the Modified Ranking Scale and the NIHSS scale. Now, these are the demographic results of our cohort. As you can see, we included 52 patients. And there was no significant difference between male and females with regard to age and education. There was a ratio of infarction and bleeding within 85% to 15% bleedings, which is comparable to cortical strokes. With regard to the causes of the cerebellar strokes, it was mostly small vessel disease and other causes, and that was mostly vertebral dissection. As you can see, there is a low NIHSS score, but that's probably the reason for that is that it measures more cortical stroke symptoms than it does for cerebellar stroke. Here you can see a heat map with stroke frequency per location. And as you can see, all strokes were located within the cerebellum, and we covered almost the entire cerebellum with all strokes. The results, here you can see a Dutch version of the frontal assessment battery, which tests more frontal executive functions, and the MoCA test, which is a general test for several cognitive domains. And what we see with the frontal assessment battery is that the mean score was 14.2, which is just above the level of a mild cognitive impairment. But if we look at the percentages, then only 12% of the patients had a maximum score. And we saw that 36% had a range at or below a level of mild cognitive impairment. When we look at the subdivision of the scores, then we saw that the least affected subtest was the environmental autonomy, which is a test that is affected with patients with severe frontal dysfunction, like frontotemporal dementia. So yeah, that's something that we don't see in cerebellar patients. The other test was the MoCA test with a mean score of 24.3, which is below the level of a mild cognitive impairment. And when we look at the several subtests, then we see that the least affected subtest was orientation, which is something you see in patients with dementia like Alzheimer's. And so that is different from the cerebellar patients. Two other tests that we did was the trill making test. With the trill making test, you make series from several numbers to connect the dots. And the second version is to connect the dots, shifting from letters to numbers. And the other test was the Stroop test, in which you have to name the color of the colors that you see without reading, so ignoring what you read. So it's an inhibition task. We saw with the Stroop test that there was a mean score of 56.2% below the normative values. And we saw that 26% of the patients scored below the 25th percentile. And when we correlated the Stroop test, which also tests the executive functions like the frontal assessment battery, then there was a significant positive correlation. But also, like with the frontal assessment battery, we also see with the Stroop test that there are not many patients that score really bad, only 2%. With regard to the trill making test, we see that half of the patients score below the 10th percentile, which is quite affected. Then we looked at several tests to see if there was a correlation between the ICAR score or stroke volume. And then we see that with the frontal assessment test, frontal assessment battery and the MoCA test, and there is a significant correlation with the ICAR score. And there is no significant correlation between stroke volume and these other tests. when we look at the fluency tests, only the phonemic fluency has a significant correlation with the ICAR score, but not the Stroop test. And there is no significant correlation, again, between stroke volume and these tests. Then we did the fluency tests and the 5-point test. The 5-point test is a sort of a non-verbal test in which you have to connect 5 dots in as many possible ways as you can think of. And there we saw that these tests were quite affected. The semantic fluency showed a 30.5% of the patients scoring below the normative value. In the phonemic fluency, it was 33.9%. And in the 5-point test, it was actually 39.2% below the normative value. Because of this significant influence or affected tests of the fluency, we also did a follow-up within time after, so at least 6 months post-stroke. And then we see that there is sort of a trend of improvement, but the follow-up does not show a significant improvement, so only a positive trend. Because there is a large difference between children and adults with regard to fluency and language problems, as we can see with the cerebellum mutism in children. We also subdivided the fluency test per age group, but we couldn't find any significant difference. Although I must say the group of 20 to 39 has very low fluency results. And in that group was also one patient of all 50 patients that showed a cerebellum mutism for a couple of weeks. Now, if we put all tests together, we did this by calculating a z-score, which gives an impression of the severity of the outcome of the tests. So the z-score from 1 to 2 is a clinical impairment, and below the 2 is a pathological impairment. And so we see that all tests reach a clinical impairment, and the semantic and phonemic fluency show even a pathological impairment. And furthermore, there is a significant positive correlation between the semantic fluency and the non-verbal fluency. So that suggests that this fluency is not only a language problem, but also might be an executive problem. We also looked at the differences between men and women, and we see that the odds of the cognitive disorders tends more to women compared to men, and this is specifically in phonemic fluency, which is was the only test that was really significantly affected more in women. And I must notice that there is no significant difference in ICAR score, stroke volume, or stroke etiology between men or women, so that cannot explain the difference.
Ruben, would you mind giving us an example of semantic and phonetic fluency?
Yes, so in the semantic fluency, you have to name as many animals, for instance, or occupations in a certain time. And phonemic fluency is you have to give a list of words beginning with an F or an S, something like that. So to conclude this part, we see that cognitive impairments after isolated cerebellar stroke are found in several cognitive domains. And as you saw in the previous slide, all tests were in a way affected. But semantic and phonemic fluency are most affected in cerebellar stroke patients. And that is something that is why during the study, I decided to also ask Djaina to help analyze the linguistics of these patients furthermore, and that's her part of the talk. Also, we saw that verbal deficits are age independent, but show a long-term effect post-stroke. And that's also quite interesting to look further into, especially the difference between children and adults. And in general, we saw that cognitive disorders after cerebral stroke are more prominent in women than in men. So now Djaina will tell you about her findings regarding the linguistics of these CODECS patients.
Okay, we're going to change our seats. So now I will zoom into the language part. And before doing so and showing the results of that part, I would like to give you a short background of what was known about aphasia and cerebellar lesions. Here I would like to show you a very important case report that was published in the 90s by Mariën and colleagues. And what they reported here was a case report of a 73-year-old right-handed woman who had word-finding complaints due to cerebellar lesion, and apart from word-finding deficits, she also suffered from spontaneous speech initiation problems, difficulties with expressive and receptive grammar, so producing and understanding sentences. And she also had difficulties with reading and writing. And SPECT analyses showed that hypoperfusion was found in the right cerebellum, but apart from that, also a prefrontal region in the left dominant hemisphere was highlighted. So it was actually very, very important. And in the follow-up phase, they found parallel patterns of perfusion change and neurolinguistic results. And this case report underlined a possible lateralized linguistic cerebellum. And after this case report was published, a lot of other papers followed, underlining and providing evidence for this lateralized, asymmetric, not also neurocognitive, but also linguistic cerebellum. And in summary, what these papers showed in both healthy participants, but also in clinical cases, that the cerebellum is associated with different aspects of language, such as phonology, which is sound, which is mainly administered via word repetition tests, verbal fluency, as you've heard already, morphosyntax production and processing, which is grammar, prosody, and reading and writing. So, as Ruben also showed, is that it could be due to a parallel system to fine-tune behavior, including language, rather than generating direct output. And due to this parallel system, the deficits may be more subtle than lesions in the cortex. Well, specifically zooming into language, it may be the case that we also miss something, even though evidence has been found that the cerebellum is associated with language function. Maybe we are missing something else, as standard aphasia tests may not be sensitive enough. So our aims as for the neurolinguistic study were the following. We started including patients a year later, and we wanted to find, we want to investigate whether there were deficits in tests for aphasia, but also specific mild aphasia. And if so, we wanted to describe the characteristics of aphasia via error analyses, and we wanted to know whether this lateralized linguistic cerebellum was indeed the case. So we looked at location, and we also looked at volume. So you've seen this design before, but here the neurolinguistic protocol at 3 months post-onset is added to the scheme. So we tested our patient at 1 time point post-onset. So this is the protocol that we have used. We used 2 standard aphasia tests. The first one zooms into word finding abilities, which is the Boston naming test. This is an object naming test where patients need to name a picture with a word. The token test is the other standard aphasia test. And this is a very common and sensitive test for not only auditory comprehension, but also very important to detect the presence and severity of aphasia. And then we also administered a new test, the diagnostic instrument for mild aphasia. This is a test that we have developed ourselves, zooming into different aspects of language, which is sound, phonology, meaning, semantics, grammar, syntax. As you can see here, you see some examples of word repetition, and at the upper row, you see short words such as engineer, which becomes more complex via compounds, watermelon, which is a longer word, non-words, proboscical, and also sentence repetition. In semantics, we developed a test for odd picture out, and here the patient needs to name out loud a picture that doesn't fit a semantic category. So in this case, this is the telephone, and it needs to be done within 4 seconds. So time constraint is very important here. And as for the syntax or grammar, the patients are asked to complete a sentence via a word. So I wash my hands with soap or water, or we ask the patient to fluently complete the sentence with a constituent, so part of speech. At 5 o'clock, well, here there are many options, and here the patient needs to construct a grammatical and semantically sound sentence. You've seen this test before, trill making test A. As time constraints are important in our language test, we decided to also take into account some test scores zooming into non-linguistic attention and processing speed, such as trill making A, here where the patient needs to connect the numbers as quickly as possible. So these are the demographics. In our subgroup, we included 43 patients. And as for location, you can see that left and right is more or less equally distributed. So now you can see the results. Here we have converted our raw scores of the tests into z-scores. And here -2, as you have seen earlier, is indicated to show a pathological impairment. And at the left side, you can see the standard aphasia test, and at the right side, you can see the subtest for DIMA. And if we look at statistical differences of the patient group as opposed to normal population, we see that there are significant differences. As for the standard tests, patients significantly differ to normal population on an object naming test, BNT, and on the token test. And as for DIMA, they are significantly better actually in the repetition of words. They are significantly worse in repetition of sentences, semantic off picture out, and sentence completion. And if we look at the pathological impairments, then the last two DMA tasks are impaired. So semantic off picture out and sentence completion. We also looked at correlations with the token test, as this test is very important to detect the presence and severity of aphasia. And there we see a moderate positive correlation of repetition of sentences and sentence completion. There was a weak positive correlation of the semantic off picture out with the token test. If we zoom into the errors that the patients have produced, in total, we have zoomed into the different categories. And here we can see that semantic paraphasias occurred most often. And I will give you some examples in a bit, but this is very striking that semantic paraphasias were in general very prominent, followed by subordinate words. So for instance, furniture for table. Phonemic paraphasias were also very common, followed by other categories which were less frequent. So now I would like to show you what we found per test and what the top three was as concerned error category. And for the object naming test, Boston naming test, so here you can see a picture of a harp, and we see that semantic paraphasias were most common. For instance, patients would say trumpet for harp. Circumlocutions were followed after the first category. So for instance, circumlocution is a description of a picture. So here a patient would say, this is a musical instrument with snares, and it's not a guitar. And anomia is a word finding deficit. So here the patient would think for a while before producing the correct word. For sentence repetition, we see that hesitations were quite common. These were followed by phonemic paraphasias and irrelevant paraphasias. An example of a phonemic paraphasia is a substitution of a sound. So here in Dutch, this would be a sentence like, de piepende wielen hielden hem uit zijn slaap, where the patient would say, de piepende, piepend wielers. So the patient here substitutes different sounds of the target words. And this could be followed by self-corrections or not. That can be different. As for irrelevant paraphasias, here a patient would say a different unrelated word. For the semantic off picture out, we see that the wrong item selection is most common, followed by a slow reaction, so a reaction that lasted longer than 4 seconds, or no reaction at all. So semantic error, a wrong item selection would be here, a patient would say watch, for instance, instead of telephone. So because we were interested in the reaction time, and slow reactions was the second most common error category, we did a correlation with trill making A, which taps onto processing speed, non-linguistic processing speed, which you have seen, which was a test which was impaired as well in our larger group. However, we didn't find a correlation with trill making test A. So it seems to be that this slow reaction is linguistic based. As for sentence completion, also slow reactions were very common. They occurred most frequently next to syntactic errors, and also perseverations occurred. Here, we also looked at possible correlations with trill making A, and here, again, this wasn't the case. So no correlation with a non-linguistic processing speed task. As for syntax, what the patients would produce here, when completing a sentence, they would omit, for instance, obligatory articles such as the or a or an, or they would omit obligatory subjects such as he, she, or they in the sentence, or no verb inflection would take place. So when looking at some clinical variables on the deviating test scores, we looked at lesion location, left versus right, and we looked at lesion volume. In our cohort, we didn't find any influence. We didn't find a relation between lesion location nor lesion volume. So to sum up, we did find and underlined a cerebellar aphasia in our group. And we did this via the finding of deficits in standard, but also new subtests for mild aphasia. And if we look into the different linguistic modalities, deficits would take place at production level, but also at comprehension level, at both the word level and at the sentence level, and at different linguistic levels, such as phonology and syntax, but most prominently in the field of semantics, which is meaning. And this was attested by the high occurrence of paraphasias. So the guitar for harp, for instance. We didn't find any influence of non-linguistic processing speed on the deviating tests. However, we didn't look at verbal working memory. So what could the underlying mechanism be in terms of cerebellum and semantics? Could this be a uniform prediction system? Well, it has been known, and the theory of the symmetry of thought is very well known in this audience, especially related to ataxia and the coordination of complex movements where overshooting or undershooting takes place. This may be happening in the linguistic domain as well. Maybe it is error-based, and patients need to monitor the intended and the perceived outputs via their paraphasias. Or maybe it could be the case that there is a disturbed linguistic prediction system, or maybe there could be a disturbed control system related to language. And we especially saw this in the sentence completion test, which was the most sensitive test of DIMA, where slow reactions took place. Here, prediction and or inhibition could also have played a role. For instance, when you see the example here, I wash my hands with versus every day, the construction and the grammatical aspects of the sentence that was given sort of predicts what would be coming in semantic aspect, but also into grammatical aspect. And the occurrence of syntactic errors may point to a more pure syntactic deficit, but we don't know that yet. So as for lateralization, so in this cohort, we didn't see a lateralized linguistic cerebellum. It could be the case that a more detailed division is needed, as the literature also pointed into associations of specific parts of the cerebellum, which was associated to linguistic disorders. It is the case, however, if this is clinically feasible. So for our cohort, it may be a bit too difficult to do that. Or it could be the case that there is no lateralized linguistic cerebellum, but it could be the case that there is an integral cerebral interaction with eloquent cortico-subcortical areas, such as the inferior frontal gyrus, which is associated with word finding at subcortical level, the arcuate fasciculus, which is associated with phonology, or the inferior fronto-occipital fascicle, which is related to semantics. This could be indeed the case. There are some limitations, though. Our linguistic investigation only took place at 3 months post-onset. So we didn't look at this at their test scores, and we didn't administer the neurolinguistic protocol at 6 months. So far, the linguistic protocol didn't contain any reading or writing tests and no working memory. And of course, 43 patients may not be enough to look at laterality, but the data collection is still ongoing. For the future, we aim to look at some semantics and also some spontaneous speech and syntactic tests. So it could be interesting to look at the errors that they produce more thoroughly. And we also would like to look at a comparison with other isolated pathologies, such as a patient tumor population. So for this part, but also for the neuropsychological part, we can conclude that patients with isolated cerebellar stroke do suffer from cognitive deficits with emphasis on language deficits, which may be mild aphasia, but also a normal aphasia. And for the clinic, we advise to administer an extensive interview, at least with respect to language complaints, in order to see if the patients, if you ask detailed questions, if they do encounter differences as opposed to their pre-stroke time point. So we do recommend to administer a short neurolinguistic screening protocol, including complex tests with time constraints in at least the first months post-onset. So we would like to thank our team and of course the patients and family in the first place. And here, this is the red arrows indicate where Ruben and I are located. I am located in the office in the building to the left at the 21st floor. And Ruben is located in the building to the right. His office is there at the 22nd floor. Well, thank you for your attention, and we are happy to reply to some questions.
Thank you so much. And Ruben, that was wonderful. Please just raise your hand if you have a question for Djaina and Ruben. I'll start out. I was thinking about the consistency between the naming deficit, the Boston naming deficit that the patients showed, and the semantic and fluency test where they had to name words that began with some letter, and also what you said about sentence completion. So it seems like there's some issue with finding the right word, searching the memory space for that word. I wonder if you can comment about that.
Yes, indeed. So what we see here, that there are different possible underlying reasons here. Time constraints play a very important role. As in verbal fluency, the patients are asked to come up with a list of words within a specific category, which is 1 minute. So this is a time constraint. With sentence completion, we also ask the patient to fluently finish the sentence. If the patient takes more than a few seconds to finish the sentence, we score it as incorrect. So it's a very strict test. And also for the semantic odd picture out, here we find different errors. So not only a slow response, which may point to word finding deficits, also the wrong item selection was an error category. So I think it can be a mixed. There can be mixed reasons here, also due to the semantic paraphasias that were occurring. It is very interesting to look at the specific errors that the patient made in sentence completion, and maybe see if they produce also words from a different semantic category, or come up with a non-semantically sound constituent or a grammatically incorrect constituent. Only then you can see whether it is a problem of overshooting, undershooting, I think, or the specific semantic errors, the semantic underlying errors. Because if you can see, for instance, errors which are in the semantic domain, in that case it may be more linguistic related. Whereas if the patient takes more time, then it is still a bit unknown, and maybe we need to look at other tests which are non-linguistic in order to see some correlations and see if we can find a pattern there.
you mentioned that in sentence completion, which kind of requires a prediction, they were particularly affected. And I was thinking in children, one way to measure in infants, one way to measure their ability to detect an error, an unexpected event, are physiological responses that they show. And I wonder in your patients, if you could consider measuring the detection of an unexpected event during a sentence, so a word that was unusual at that location.
Yes, that will be very, very interesting. And there are a few studies using this type of design. We have worked on this experiment as well, which is ongoing. We have developed an eye tracking test where a sentence completion task is actually implemented. The first part of the sentence is said out loud and is also visualized on the screen. For instance, I wash my hands with, and then there are 4 pictures shown in each corner. So in 3 out of 4 corners is semantically a potential response is visualized, rating from highly feasible to less feasible. This was done via a survey, though. We asked healthy participants to give a scoring to these items. And then in one corner, a non-semantically response is visualized. So I wash my hands with telephone, for instance. And we are very interested to know how our patient group will respond to this, and if they will look first at the target, which doesn't match at all, or maybe shows some other patterns, such as looking at the least feasible semantically sound option. So this we don't know yet. We do think that our patient group would differ to a normal population. Maybe patients without cerebellar stroke would be faster and may look in less saccades to the right corner of the screen. We're also interested in inhibition, asking in the same type of experiment, asking the patient to reply with the non-matching reply in this context of the sentence completion task. So this, there could be some interesting findings here in this type of experiment. And this was also done by Lesage and colleagues, but then in fMRI. So yeah, we are trying to replicate that in our group in a different type of, with eye tracking.
Wonderful. Are there any questions for Djaina and Ruben? Yeah.
Hi guys, thank you for a lovely talk. I was wondering, in any of your patients, did they exhibit any motor-related speech deficits like dysarthria, for example? And did you find that those symptoms correlated strongly in severity with the severity of their aphasia?
We did do the ICAR score, which also has an item on dysarthria. But there weren't really severe dysarthria patients. And as I showed you, there is a correlation between the frontal assessment battery and the ICAR score, and also the MoCA. So there seemed to be some influence with regard to the language. Djaina, I don't know if you can answer that.
So with word repetition, of course, a patient could make an error due to a dysarthria instead of an aphasia. I did look at those differences. And most of the errors that I saw were language related. So the difference between a dysarthria and a phonemic paraphasia is with a phonemic paraphasia, there is a structured pattern of substitution of sounds, whereas in dysarthria, it's a slurred speech So and then it's more general, general problem in the outputs. We did take that into account. I didn't show you these results on the slides, but this is the way we did the qualitative analysis based on error analyses. It is, of course, interesting to measure the level of dysarthria and maybe speech apraxia, ataxia more elaborately. So we did add a tool for speech apraxia to our protocol, but we don't have that many patients yet with these test scores. So maybe in the future we will be able to show that to you.
I think the underlying question is probably whether the motor symptoms influence the non-motor or the cognitive things. And I think that there will be, of course, a correlation. So patients that are more severely affected with the motor symptoms will probably also have worse cognitive outcomes. But I think in our study, we don't see that the cognitive problems, the deficits, are caused by the motor problems.
Lovely, thank you.
So I had a question about the semantic overshoot. I was really interested in that. And one thing that I know I've read about is that in NLP, they can do words as vector embeddings, and those distances can capture some semantic meaning. I wonder, would there be a way to try and look at the choices that patients make when they replace a correct word with an incorrect word, and then see if there's a way to assess the magnitude of that overshoot? Is it something you guys have tried to look into?
I think this relates to the experiment where we are, which is developed.
Ongoing.
It's ongoing,
Yeah.
and I think what we would be able to say something about the level of over or undershooting, because in the item design, so the example that I just gave with the 4 corners and 4 words, which 3 would be possible in the sentence completion task and the 4th would not match. These other 3 were actually developed via a survey. So we asked our healthy participants to rate how likely the word would be in that sentence with a scale from 1 to 5. So we would be able to say something about the specific response that the patient would give in terms of semantic, I would say, predictability. Yeah, via a rating scale, indeed. So this is something new, and we developed it ourselves. So yeah, I won't be able to say something about this right now, but I think we will be able to be more specific when we have the results of this study.
All right, that's really exciting. Thank you so much.
Wonderful. Well, thank you, Djaina. Thank you, Ruben. It was a real pleasure learning from you, and just kudos to you for this incredible 10-year study, and I hope that you will continue it. And thank you for taking the time to telling us about it.
Thank you for the invitation.
You're welcome. Thank you.
Bye, everyone.
Bye-bye.